Let's start the next topic, that is the numeric codes and the subtraction of the binary and digital numbers. First of all, before going to the numeric codes, we'll have a brief or the precise working of the digital numbers and the arithmetic operations that can be performed on the number systems. The most important arithmetic operation we perform on the number systems are addition and subtraction. Addition, of course, can be performed in a normal way, like the way we do in the regular math. But in digital systems, the subtraction cannot be directly performed with the normal procedure. So what can be the procedure to perform the subtraction for the digital numbers? So the answer is, we find out the complements of the numbers, and then we add the complement of the number to the number from which it is subtracted. Okay, so I'll illustrate you with a brief example about the subtraction with complements. Let's start the first step, subtraction with complements. Complements are used for simplifying the subtraction operations. That is, in digital number systems, we cannot directly subtract. Hence, to simplify the subtraction operation, we can perform the subtraction by first finding the complement of the number which is to be subtracted, and then adding the complement of the subtractand to the number from which it is added. So before going on to the types of complements, I'll just illustrate you with the rough idea about how can the procedure be performed. Let's take an example. Let's say x is subtracted from y. First, I'll start with x plus y. X plus y, since it is an addition, we can directly perform the addition with the normal procedure. That is, we don't need to take any complements here, and hence the regular operation can be performed. Now let's start up with x minus y. X minus y, here the operation cannot be directly performed by the regular math. So to perform the operation of x minus y, first we have to take the complement of y. The complement of y, let's say y's complement is a. Okay, so after we obtain the y's complement, which is a, we can add x plus a. That is, we can add a to x, and the resultant obtained is equal to the answer of x minus y, where a is the complement of y. Similarly, we can perform various other operations by different bases and different complements. Let's go into detail about how the complements can be performed, what are the types of complements, and what all complements can be executed in what conditions. Let's say, for example, first we'll start up with the complements and subtractions. There are two types of complements for each base R system, the R's complement and the R minus 1's complement. What here R means? For example, let us say if R is 2, okay, that is the base R is 2. So here we can obtain 2's complement as well as 2 minus 1, which is 1's complement. So similarly, there are total of 2's complement, 1's complement, which this two combines for binary numbers, and for decimal numbers we have 10's complement and 9's complement. That is, R's complement, which is 10, and R minus 1 complement, which is 9, which are again for decimal number. So we'll study in detail how to find out the procedure for complements. The 9's complement of the decimal number, first is the 9's complement. How it can be obtained? The most simple and the important step here is subtracting any number for whom which we are asked to find out the 9's complement by 999. Let's say, for example, a number is 546700. If we are about to find, or we are asked to find out the 9's complement, then simply we have to do is we have to subtract 546700 by its equivalent number of 9's. For example, in this case 546700, total number of bits here are 1, 2, 3, 4, 5, 6. That is 6 numbers. This itself has 6 bits. So to find out the 9's complement of this number, we'll have 9 bits. 1, 2, 3, 4, 5, 6. Sorry, for this number we'll be having 6 9's. So after subtracting 546700, The resultant show obtained, that is 453299. It is the 9th complement of the number 546700. Similarly, let us take the other example, the 9th complement of 012398. Here total are 1, 2, 3, 4, 5, 6. Total 6 bits present in this number. So we'll take 6 number of 9s, that is 1, 2, 3, 4, 5 and 6. So we subtract this number 012398 with 999999, and the resultant show obtained 987601. This is the 9th complement of the number 012398. The next is to find out the 10th complement. As we have the rough idea that the 9th and 10th complement are directly for the decimal number systems, so we'll again go for the way to find out the 10th complement. We'll just study the procedure first. The 10th complement can be formed by leaving all the least significant zeros unchanged, subtracting the first non-zero least significant digit from 10 and subtracting the higher significant digits from 9. Okay, that is 012398. The 10th complement of the number is 98762. That is, as we can see from the previous 9th complement 012398, the 9th complement was 987601. Similarly, for this number, the 10th complement is 987602. So the whole story in short can be termed as, to find out 10th complement, first we have to find out the 9th complement. After finding out the 9th complement, the number obtained, which is the 9th complement, just needed to be added to 1. So the number added to 1 and the resultant gives the 10th complement. That is, adding 1s to 9th complement gives the 10th complement. Now the next one is 2's complement. 2's complement are used for binary complement or binary subtraction, we can say out. So we'll just read out the step and then I'll explain you in detail what are the 2's complement procedures and how we can find out. The 2's complements can be formed by leaving all significant zeros and the first one unchanged, and replacing ones with zeros and zeros with ones in all other signed significant digits. Let us take the example of this, the 2's complement, to find out the 2's complement of the number. Okay, so the 2's complement of the number is the 2's complement of this number 1101100 is 001010. I'll just explain how this comes. The number is 1101100. Okay, so as the procedure says, first we have to go from right to left in this direction. Since the first bit is 0, we write it as 0. The second bit is 0, again we write it as 0. Now it starts from this 1. The moment we find the 1 after the zeros, we write this as 1. That is, initially zeros remain unchanged till we find 1. The moment we find 1, we write the 1 as it is, and after this 1 we keep on finding the complement of the numbers which we come across. That is, initially these two zeros remain unchanged. This 1 we have found out the 1 after zeros. After the first one, which is the first one in this number, after this first one we start taking the complements of all the bits which are present to the left of this one, so we write this number as it is. Then for this number we write its complement, the 1's complement, that is, we replace 1 by 0, we replace 0 by 1, we replace 1 by 0, and we replace again the last one by 0. That is, this is the 2's complement of the number. That is, first we try to find out 1. So we don't take the complements till we find out 1. After we find the first one in the bit from right to left, we start taking the complements of the bit after that number. Hence, this is a 2's complement of this number. Similarly, 1's complement can also be found out the same way. Let's say 100101. 1 0 0 1 0 1. Let's take the example of this. Unlike in 2's complement, here 1's complement is like we can directly take the complement of all the numbers what we obtain here. 1's complement is 0, 0's complement is 1, 1's complement is again 0, 0's complement is 1, 1's complement is 0's complement is 1, and 1's complement is 0. Let's discard this. So the 1's complement of the above number is this 0 1 1 0 1 0. That is, we can see from the example that to find out 1's complement, we just simply have to change the bit. That is, if 1 is there, replace 1 by 0. If 0 is there, replace 0 by 1. 1 is there, replace 1 by 0. Replace 0 by 1 in this case. Replace 0 by 1 and replace 1 by 0, which is the 1's complement of the number. Now, let's study the procedure for subtraction with complements. As we have studied that the subtraction are done only by finding out the complements of the number which is to be subtracted and then adding the complement of the subtractant to the main number from which the number is to be subtracted. The subtraction of two n-digit unsigned numbers m minus n in base r can be done as follows. That is, as I told you, first step is to find out the complement of n. After finding out the complement of n, either it's 1's complement, it's 2's complement if binary, or if n is a decimal number, the complement can be either 9's complement or either 10's complement. So for example, let us assume that r is a binary number. So we can execute m minus n by first finding out the complement of n. That is, either we can find out the 1's complement of n, or we can find out the 2's complement of n, and after finding out the complement of n, we can add the number to m. That is, which gives m plus complement of n. Now again, here in this case there are two criteria. Now first, if m is greater than n, and the second criteria, if m is less than n, that is, the number to be subtracted is greater than n. If m is greater than n, then as per the regular math, the answer will be positive. Okay, and we can discard. And if m is less than n, that is, if m is less than n, then the final answer will be negative. So let us take the first step, that is, if m is greater than n, then what will be the result and what all bits can be retained and what bits can be discarded. If m is greater than n, then sum will produce an end carry r raised to n, which is discarded, which is left. That is, if m is greater than n, then we can find out the carry. Carry as in, like, if m is greater than n, then first step is we find the complement of n, and after finding the complement of n, we add it to m. Okay, and if the end result is carry, then the carry 1 is discarded and the left result is m minus n, which shows that the m is greater than n. Let's take an example. 5 minus 4. The decimal equivalent of 5 is 1 0 1, and decimal equivalent of 4 is 1 0 0. We cannot directly subtract this, so first we take it by 1's complement. Okay, so the 1's complement says that replace 0 by 1, replace 0 by 1, replace 1 by 0, which is the 1's complement of 4. So we add 1 0 1 plus the 1's complement of 4, which is 0 1 1. That is 1 plus 1. In binary addition, in digital addition, 1 plus 1 never gives 0. 1 plus 1 always gives 0 with a carry. Similarly, 1 plus 0 is 1. 1 plus 1 is 0. That is, again, addition of this, 1 plus 1 gives 0, carry 1. 1 plus 1 gives 0, carry 1. Since it is 1, carry is 1, that is, m is greater than n. Since m is greater than n, the carry n1 can be discarded. Therefore, the result obtained is 5 minus 1. Now let's move on to take on the other example, the other criteria. If m is less than n, then the sum does not produce any n carry. That is, if m is greater than n, the sum does not produce any carry, so the final answer will be negative. That is, to obtain the actual exact answer, if there is no carry, we have to take the complement of the end result, as the number itself is negative. We'll understand this with the help of an example. Let's say, for example, 4 minus 5. Okay, so let's take the binary equivalent of 4, 1, 0, 0. 5 is 1, 0, 1. Since m is greater than n, the answer should be negative. So let's find the complement, ones complement of 5. That is, since 5 is a subtractant, we find out the ones complement of 5, which is 0, 1, 0. So adding 1, 0, 0, which is 4, plus the 5's complement, 1's complement of 5, 0, 1, 0, which gives 0, 1, 1. There is no carry, as you can find out. Since m minus n is negative, there won't be any carry. That is, the end result is 0. The end result is 0, that is, the answer is negative. So we have to take the ones complement again to find out the original answer. So replace 0 by 1, 1 by 0, 1 by 0, and this 0 shows minus. Okay, that is, the answer of 4 minus 5 is minus 1.